Okay, so today we're going to start a brand new chapter. This one's going to be on graphing sine and cosine. So we're going to actually look at what the graphs of both sine and cosine look at and how they can actually be used for a bunch of different real world situations. But for today, we're just going to focus on what those graphs look like. So today's plan, covering trigonometric graphs, we're going to discuss the shape of the graphs of sine and cosine functions. We're going to talk about key features of trigonometric graphs, and we're going to look at vertical stretches and horizontal stretches of these functions. Now, just kind of for your information here, we're only going to very loosely follow the notes booklets, the ones that are uploaded on Google Classroom from here on. I'm not going to rely on them anymore. And the main reason is because the booklets are a little bit too full of content, and we won't have enough time to get through it all. So I'm going to focus on trimming down exactly what we need to know. Feel free to use those booklets as a resource, though they are available for you. If you want my advice, take point form notes while watching these videos. Definitely be jotting something down, especially in this chapter, which has a lot to do with graphing. You do need to gain some experience at actually graphing these. So having graphing paper and a ruler or straight edge would be very useful. Anyway, let's get started here. So sine and cosine, right here on the page, you can see what the functions look like. Sine, of course, is on the left and cosine is on the right. The trigonometric functions sine and cosine are considered periodic functions. Now, periodic is just a fancy way of saying there's some sort of repeating pattern. And if you look at these, even if I follow my pen over them, you can see they follow a repeating pattern. There's a peak and then a trough and then a peak and a trough on both of these, right? Now consider the angle theta that we would usually plug into sine. So sine of theta, for instance. Consider that being your x coordinate here, so it's along your x-axis. And then the value of the trig ratio itself, so actually if you plugged in that angle into sine or cosine, to be the value of your y-axis, right? From here on out, we're mostly going to be just calling it x instead of theta in here. And the reason being is oftentimes when we look at real world situations with these, we're not actually throwing an angle into sine, right? We're actually throwing just some sort of value. Oftentimes it's time, right? Don't worry about that too much, though. We'll get that a little bit later on. But for now, just understand that sine and cosine have a periodic form to them, right? Now, the length along the x-axis of one complete cycle is called the period. So one complete cycle, you can use a bunch of different points to kind of denote that. You could use like the midpoint going up to the next time you have a midpoint going up, and notice that distance is 2 pi or 360 degrees if you're using degrees. Usually we're going to be using radians here, but degrees come around every now and then. You could also consider it a peak to another peak, right? So from one peak to another peak, it's 2 pi. You can consider it a trough to another trough. Really, pretty much anything you want, you can consider that the period, as long as it's from the same location to its other same location on the same graph. Now, the height above the midline, of course, being the horizontal line that cuts these straight in half, that's called the amplitude. So regardless of whether you're dealing with sine or cosine, your amplitude is going to be 1, right? So from your midline to your maximum, that's 1. Now, the other thing I'll say about amplitude is, amplitude, generally speaking, we always consider it a positive number. You wouldn't say you had a negative amplitude, but we will look at a question a little later on today that does have a negative amplitude piece to it. But we actually will still look at that as being a positive amplitude. I'll get to that when we get to it. The other thing I want to mention on this is, notice that, let's say if you looked at one of your maximum points and then the next maximum point, notice that right in between those two is your minimum point. That's not a coincidence, right? So in other words, that does tell you that right in between your maximum point, you have minimum point. And the reverse is true as well, right? Between two minimum points, you also have a maximum point. Another thing that might be useful to note is if you look at your midpoint going up, or in other words, your x-intercept on these, your midpoint going up to your other midpoint going up, right in between those is another midpoint, but it's a midpoint going down, right? You can say the same thing about two midpoints going down. You have a midpoint going down and a midpoint going down. Right in between those is a midpoint going up. Those are important things to kind of note. Those are some very key features of these graphs. Now, for sine and cosine, another thing we connect this to, this is kind of just an interesting connection. You could consider cosine to be x and sine to be your y. Remember last chapter, I did say that at least on a unit circle, cosine spits out your x value and sine spits out your y value. This image is kind of cool here. If you track it as it goes around the circle, you can see that cosine, the value of cosine of that angle, is just spitting out your x value. So it's 1, and then it's 0, and then it's -1, and then it's 0 again, and then it's up to 1. Whereas sine is spitting out your y value. So if we watch as it comes around, notice y is -1, and then y is 0, when you have an angle of 0, of course, and then 1, and then 0, and then -1, and then 0. It just repeats a pattern. So sine, of course, is your y, cosine is your x. That's just another way of thinking about that. Whether that's useful to you or not, that's up to you. Moving on, so sine and cosine, there are a few other features of these graphs that you should take note of. One thing is that these two graphs are pretty much the exact same thing. It's just they're shifted left or right depending on whether you're using sine or cosine. So if we want to look at sine, first of all, I want you to notice that when x is 0, which is usually what we would consider our start point here, when x is 0, we're starting at our midline going up. So when x is 0, y is 0, right? Whereas if we're looking at cosine, when x is 0, we're actually starting at our maximum point, which is y is equal to 1. The other thing you can take note of here is for both graphs, the x distance from a maximum to a minimum is just half of what that period would be. So it's just pi, or in other words, 180 degrees. That would be really useful to remember as well. Now, first of all, we're going to start talking about vertical stretches and amplitude. There is a direct connection between these two. Now, I want you to recall this is from the very beginning of this year, that in function notation, a vertical stretch by a factor of a occurs when you have y equals a times f of x. Now, a vertical stretch multiplies all of your y values by that a value. So in other words, this is going to affect how tall your graph is, or with these situations, with trigonometric graphs, it's actually your amplitude, right? Your a value is your amplitude. And I think that's really convenient given that they both start with letter A, of course, as dumb as that sounds. I want you to compare the graphs of y equals sine x and y equals 2 sine x, and I've done them in degree mode. I just threw them in an online graphing software. Notice that on y equals sine of x, we just have our normal sine wave where we're at a maximum of 1 and a minimum of -1 down here. But when we multiply the outside of it by 2, we're vertically stretching it. And our amplitude now becomes 2 instead of 1. So our amplitude is going to be equal to that a value. The other thing that's really important to note with this is that when you do a vertical stretch, your x-intercepts aren't going to move, right? So they're still at 0, 180, and 360 on these ones. And the reason they don't move is actually because, remember, a vertical stretch just multiplies your y values by a. Your x-intercepts have a y value of 0. If you multiply 0 by any number, they're not going to budge. It's not going to change whatsoever. So in other words, when you do a vertical stretch, you're only changing your amplitude, which are your y values. You're not changing your x-intercepts whatsoever. So for a quick example here, compare the graphs given by the domain, or given the domain 0 is less than or equal to theta, which is less than 2 pi. So this is just the domain we're working in here. Let me kind of break this down for you. I'm going to start by doing a really rough sketch of each of these two graphs, sine theta and y equals 3 sine theta. First of all, we know we have to operate within this domain. So since that's dictated to us, I'm going to say that the edge of this is 2 pi on both of these graphs. The other thing I want you to remember is I told you in the last slide that amplitude is your a value. So on y equals sine theta, we're going to have an amplitude just of 1. In other words, the maximum point from the midline that it's going to go up is just at 1. Now, I'd like to make my scale the same on both of these little graphs here. So I'm going to say 1 is just down here, which would mean 2 is about here and 3 is up here. And I'll do the same scale as best I can on both of these graphs. And of course, we'll do the negatives here as well. So 1, 2, 3, -1, -2, -3, 3, 2, 1, -1, -2, -3. Okay, so the other thing I want you to take note of, because we'll start with this y equals sine theta, sine starts at your midline going up. So in other words, right where x is 0, you're starting at that midline, and this is going to be going up from here. But I don't want to start drawing this until I have a little bit more information regarding this. Now, we know with sine theta, it has a period of 2 pi. So in other words, at 2 pi, you are also going to be at a midline going up, okay? Let me just erase that just so it doesn't stick around. But you're also going to have a midline going up right there. Now, earlier on, remember what I said, when you have a midline going up and a midline going up, right in between those two, you're going to have yet another midline, but this one's going to be going down, okay? So remember, we want to have a complete cycle where we start back where we started after 2 pi. Now, since we have a midline going down here, logically, in between this point and this point, we're going to have our maximum. Because again, we have to have a midline going up at the beginning, so it's going to reach its maximum, come down, we'll have a midline going down, and then of course between these 2 points, you'll have your minimum. Now you can very clearly see an outline of what our graph is going to look like here, and I'm just going to do my absolute best to try to sketch this. It's not easy with this pen tablet I've got. but that is a decent, honest try, right? That's not too horrible. So that right there would be a good sketch of this graph. And if I wanted to fill in all these points, this point being between 0 and 2 pi is going to be at pi. This point between 0 and pi is going to be pi over 2. And then, of course, between pi and 2 pi, it's like pi and a half, or in other words, we would call that 3 pi over 2. Okay, just nice to like label those in. Now, as for y equals 3 sine theta, remember what this is doing is it's changing our amplitude. Instead of having an amplitude of 1, we're actually going to have an amplitude of 3 instead. Now, the other thing I want you to note is your x-intercepts are not going to change. So right off the bat, I'm going to say, you know what? This x-intercept is going to stay the same. Same with this one here and this one here. So those aren't going to move because, again, their y value was 0. However, my maximum and my minimum points, those are going to change. So my maximum, which occurred at pi over 2, isn't going to be 1 anymore. I'm now going to have an amplitude of 3, so it's going to be bumped way up here. And then likewise, at 3 pi over 2, we're going to have a minimum way down here. Now we can see an outline of our graph. So once again, I'll carefully try sketching this. It doesn't have to be perfect, just as good as I can reasonably get it here. And that's going to work just fine. And again, I'll label all these two just for good measure. Awesome. So now that I have these sketches, it's going to make filling out this table a lot easier. If we look at y equals sine theta, the first one here, what would our period be? Well, our period is how long one full cycle is. So our cycle here is 2 pi. Now, when we multiplied sine theta by 3 on the outside here, did that change the period? Well, if you look, we see an amplitude going up, or sorry, a midline going up and a midline going up. So no, that didn't actually change our period at all. So we still have a period of 2 pi. Now our range, however, remember a range is your minimum to your maximum y value. The range of the original sine function is from -1 to +1. However, the range of this other sine function is from a minimum of -3 to a maximum of +3. So that absolutely did change. Notice how my range is dependent on that amplitude. That's an important thing to remember. And of course, that takes us to amplitude. This is probably the easiest question they've asked us. The amplitude of the original is, of course, 1, because that's what all sine and cosine graphs are. But for 3 sine theta, the amplitude is going to be 3 instead. We're going to do another example really quick here. Hopefully I'm not beating this to death. We're going to do one with cosine, though, still within the same domain. So like before, I'm going to set my domain perfectly clear on both of these graphs. Now, before I start labeling my y-axis, once again, I'm going to look at my amplitudes here. This one has an amplitude of 1, and this one looks like it has an amplitude of -1/2. But remember, amplitudes are usually, or not usually, they're always listed as a positive number. The only thing that this negative is doing is it's a negative vertical stretch, which, if you remember from the beginning of this course, is actually a vertical reflection. So this one will actually be vertically reflecting it upside down. We'll worry about that a little bit later. Let's focus on actually getting our cosine graph drawn first. Now, what you need to remember about cosine is that it starts at your maximum. So when x is 0, you're actually starting up at your maximum for cosine. And cosine's maximum is equal to its, of course, amplitude, which is 1. So because this one only has an amplitude of 1/2, I'm actually going to say on these graphs that 1 is up here, which means therefore -1 is down here, and we have 1/2 and 1/2. I won't label that, but we'll again put 1 here, -1/2, or -1 down there, and then 1/2 and -1/2. But I won't label them just to save time. So cosine is going to start at your maximum. Now, cosine's period is 2 pi. So in other words, the next time we reach our maximum, because that's the equivalent position, is going to be over here at 2 pi. So again, I'll have a maximum there. Now I think about what's in between these two. Well, right in between we have pi, but at pi, notice between two maximums, you're actually going to have your minimum. And then between a maximum and a minimum, you're going to have a midline piece or an x-intercept on both of these. The only difference is this x-intercept is going to be a midline going down, and this one's going to be a midline going up. Now I have enough to sketch the graph, so I'll just fill this in, again, drawing as carefully as I realistically can. That's not actually too bad. There we go. Now let's draw this other graph. -1/2 cosine theta. Well, 1/2 is referring to, of course, our amplitude. So we're going to have a much tighter amplitude on the next graph. But this negative is really important. The negative is a vertical reflection. So instead of starting up at our maximum, we need to vertically reflect it down and start at our minimum. But our minimum isn't going to be -1 this time around. It's going to be -1/2 instead, because again, our amplitude this time is only going to be 1/2. So instead of starting at a maximum, because of this vertical reflection, I'm going to be starting at my minimum. And since I'm starting at my minimum, and this is just a vertical stretch, so it won't affect the period, my next minimum is going to be here at 2 pi, because it's going to complete one cycle to get there. Now, in between two minimums, we're going to have a maximum. So again, if we have pi right here, our maximum is going to be at 1/2. And then between a maximum and a minimum, we'll have our midline on both sides here. This one will be a midline going up, and this one will be a midline going down. And then we just connect it with our graph. This one's not looking quite as good because I'm kind of scurrying along here, but that's a decent indication of it. Anyway, let's fill in this chart now. Let's start with cosine theta. The period of that, of course, is 2 pi, as it always would be for just a plain cosine graph. But the period of -1/2 cosine theta is also going to be 2 pi. And the reason being is, again, you're only doing a vertical stretch, and if you're only stretching something vertically up and down, you're not changing how long one cycle is, right? Now the range on both of these are going to be a little bit more interesting. The range of this one, of course, since it's just cosine, is -1 to 1. But the range of this one, its lowest point is -1/2, and its highest point is +1/2. So that one will have a range of that. Notice the range is directly connected to your amplitude, which brings us to our amplitude, of course. This one just has an amplitude of 1, and this one, I would say, has an amplitude of 1/2. I don't think it's a good idea to say an amplitude is a negative number, so don't just totally put the negative there with an amplitude, because again, an amplitude just tells you how tall your graph is, and saying, oh, it's -1/2 tall, that's a little bit weird. Amplitudes should be positive numbers, so we'll leave it as +1/2. All right, so horizontal stretches now. We're going to move on to these ones. And this hopefully will go pretty quick, but recall that in function notation, again, from the beginning of the year, that a horizontal stretch by a factor of 1/b occurs when you have y equals f of bx. These were a little bit more tricky because, again, your b value is not what you're multiplying your x values by. It's not your horizontal stretch directly. You have to take the reciprocal of that instead. So a horizontal stretch multiplies all of the x values by 1/b. This is going to affect how wide the graph will be, which in turn affects the period. If you're affecting how wide a graph is, the period is going to change with it, because the period is the length of one full cycle. So I want us to compare the graphs of y equals sine x and y equals sine 2x. And again, I've done this in degree mode. Well, the period, of course, of sine x is just your standard 360 degrees. But sine 2x has a b value of 2, which means your horizontal stretch is actually by 1/2. What this means is you're multiplying all of your x values by 1/2. Now, when x was 0 degrees, it didn't move, because 0 times 1/2 isn't going to move. But if you looked at something like, say, 180 degrees, 180 degrees times by 1/2 is going to move it to 90 degrees. So notice we have a midline going down at 180, and over here we have a midline going down at 90. So that 180 degree point, the midline going down, moved to 90 degrees because we times it by 1/2. And same with our midline going up right here at 360. 360 times 1/2 is 180. So there's our midline going up. You could also look at your maximum point. Your maximum was 90, and now it's between 0 and 90, which of course would be 45. We just times it by 1/2, right? So if you thought of our period of both of these, the period of this one is 2 pi. But notice the period, oh, sorry, not 2 pi. I'm so used to dealing with radians. The period of this one is 360 degrees, my mistake. But the period of this one, the length of one full cycle, midline going up to a midline going up, is just 180 degrees. Long story short, to make this as simple as possible, your period is just going to be multiplied by whatever your horizontal stretch is, not by your b value. It'll be multiplied by 1/b, right? Just like all your x values would be. So again, the original period of a normal sine or cosine function is 360 degrees or 2 pi. You just need to multiply that by your horizontal stretch to find the new period. Let's do one really quick example on this. Compare the graphs given by the domain 0 to 2 pi. So once again, 2 pi is our domain here, 0 to 2 pi, I should say. We're dealing with cosine and cosine 1/2 theta. Let's not worry about this one at first. Let's just get the cosine graph drawn. But before I do that again for my y-axis, we have no change in amplitude here. Like there's no vertical stretch. So the amplitude of both of these should still be 1. So I'm going to make the most of my space, and I'll say it's 1 on both of these, which means we've got -1 down here. Okay? Now the other thing I want to take note of is cosine starts at a maximum point. So I'm going to draw my maximum here. And of course, because the period of cosine theta, just plain old regular cosine theta, is going to be 2 pi, we're going to have a maximum over there. And then in between the two maximums at pi, we'll of course have a minimum, and then we'll have a midline going down and a midline going up. So again, sketch that as best I can. There we go. Now as for this one, cosine 1/2 theta, I want you to take note that our horizontal stretch here, horizontal stretch, is not by 1/2, it's actually by the reciprocal of 1/2, so 2/1, or in other words, by 2. In other words, on our second graph, we're going to be multiplying all of our x values by 2. Now, this one here, where x is 0, that's not going to be affected, so I'm not going to worry about that. But if I looked at something like this point here, which of course would be at pi/2, that point is going to need to be multiplied by our horizontal stretch of 2. So pi/2, this midline going down, is actually going to move to pi. So instead of having a minimum at pi, we actually have a midline going down. Likewise, if I look at my minimum, which on the original graph occurs at pi, that also will have to be multiplied by 2, so that's going to be moved over to 2 pi. So our minimum is way over here at 2 pi. And that actually eats up our entire domain. We don't have any more domain room here, so I'm just going to draw that section of the graph. So it's not even a full cycle. We're not even seeing ourselves get back to our original point here because we're only looking at a section of our cycle. So if I'm going to look at the period of cosine theta, the period of cosine theta we should know is 2 pi, but the period of cosine 1/2 theta is going to be a lot more than 2 pi, right? We haven't even seen a full period here. We've looked at 2 pi in terms of a whole domain on this one, but we haven't seen a full period go, right? Long story short, once again, your period is just going to be 2 pi times whatever your horizontal stretch is. Or in other words, 2 pi times 1/b. And in this case, b was 1/2. So 2 pi times 1 divided by 1/2 is 2 pi times 2. So in this case, it is 4 pi. Now our range, this isn't going to be so interesting. Our range is our maximum to minimum. Within this domain, they still have the same maximum and minimum points. So our minimum on the original graph, of course, is -1 to 1, but it's also the same thing on our transformed graph. And our amplitude, once again, is our a value. Both of these just have an a value of 1. We don't bother writing it if it's a 1 because anything times 1 is just itself. So the amplitude on both of these is just 1. All right, moving on. We're going to combine these transformations here. I know I've used up quite a bit of time already, but we'll try to get this done as quick as possible, and this is important. Consider the graph of y equals 4 cos 2x, where x is between 0 and 2 pi. We have a blank graph here. We'll get to that in a second. But before we do that, let's determine the amplitude and the period. Now, the amplitude, of course, is just your a value. So our amp is just going to be 4. The period, on the other hand, takes a little bit of work, not a huge amount of work. But the period, of course, of normal cos x is 2 pi. But we need to take that 2 pi and we need to multiply it by whatever our horizontal stretch is. Where our horizontal stretch is related to your b value, it's 1/b, so it's times this by 1/2. Well, 2 pi times 1/2 is just going to be pi. So we know the period of this one is going to be pi. Now, part B here is saying sketch the graph. And we want to sketch it within this domain from 0 to 2 pi. So I got to be pretty careful about how I set up my x-axis here. Now, because we were given a grid here and we weren't just given a plain, like x-axis and y-axis on the other ones, I'm going to be really careful with these boxes. We want to have 2 pi over here somewhere, right? I don't want to just place it arbitrarily and then just arbitrarily divide it. I want to actually get my boxes to line up properly. So just estimating this, and again, just a straight up estimate, how about we say that if I looked at breaking up 2 pi into 1 pi and a pi/2 and a 3 pi/2, that would be 4 different segments. So I want to see maybe each segment could be maybe 8 boxes long. So 8 boxes long, that's 4. 8 boxes would be to here. Another 8 boxes would be to here. Another 8 boxes would be to here. Yep, that's right. And then another 8 boxes would be to here. That was a really good estimate, actually. That worked pretty well. So this is 2 pi. This would be pi. This would be pi/2. And this would be 3 pi/2. And again, I just made sure I was really careful with the boxes that were on my grid and set it up appropriately. Now, the other thing we'll be careful of here is our amplitude. Now, our amplitude is 4. How about I say that each one is 2 boxes? So we'll say that's 1, 2, 3, 4. Good enough. We didn't use up all this room, but you know what? That's not the end of the world. We don't have to worry about that. So I'll do my -1, -2, -3, -4. And then and just label it in. Really important that we label our axes here. We can't be lazy on that. All right, so to sketch our graph now that we've actually figured out what our window is going to be here, if we're going to sketch our graph, let's remember that cosine x starts at its maximum. This isn't being vertically or horizontally flipped here, so we know we're still going to be starting at our maximum point, and our maximum point, because of this amplitude, is going to be 4. So I'm going to put a dot right here at 4. Now, the other thing we know is that the period is pi. So after pi on our x-axis, we're going to be back to where we started. So after pi, we're going to be back to 4. After another pi, so at 2 pi, we're also going to be back at 4. See how I've taken advantage of both knowing where cosine starts as well as knowing what the period is? I was able to take advantage of that and start throwing in where some points are going to be on this cosine wave. Now, in between two maximum points is logically going to be a minimum point. So at pi over 2, we're going to have a minimum point at -4. And the same can be said between these two maximum points. So we'll have a minimum point at 3 pi over 2 down here at -4. Just being careful that I make sure it's lined up. Now, the other thing, we can just be really reasonable here. To get from a maximum to a minimum, we have to cross the x-axis somewhere, and it's going to be right at the midway point. And that was why 8 boxes was such a nice number to use, because 8 can divide by 2 to 4. So at the 4 box point, I can put like a little tick right here, and then same with here, a little tick right here, and 1, 2, 3, 4 right here. And those are going to be where we're crossing our x-axis. So I could actually make those ticks into dots. With that, we just have to be really careful when we draw our graph here. Try to do your best at this. So draw the slope going down like this, and then kind of a trough like this. There we go. And then a peak coming up and then coming down. Good. And then a trough. And then a peak. And you know, I gotta say, I gotta hand it myself. I think I've done that pretty darn good. And there you go. There's your sketch, right? You've sketched your graph. You can clearly see you have a maximum point that it reaches every now and then on a periodic scale of 4, and a minimum that it reaches periodically at -4, right? So that would be a good sketch for that graph. All right, so we're almost done here. I just want us to complete the table. This is, again, combining all our transformations. We're gonna look at just a domain of x is between 0 and 2 pi, with the exception of this one, where we look at it as if it was in degrees, but just bear with me on this. So I'm going to give you 2 different equations here, and we're going to talk about the transformations compared to the base function sine or cosine. We'll find the amplitude and the range, because again, those are connected as we've seen, period in degrees, period in radians. Anyway, let's look at this first one here, negative sine 6x. Well, let's think about our transformations. We don't have a vertical stretch, but we do have a vertical reflection out here because of the negative number, or the negative in front of it, right? So we can say we have a vertical reflection. So a vertical reflect. And then this 6 here is going to be a horizontal component, but be really careful with that. That's a horizontal stretch, not by 6, but by 1/6. So in other words, you'd be multiplying all of your x values by 1/6 to get that. Now for our amplitude here, our amplitude again is our a value. A in this case is -1, but we don't say we have a negative amplitude, so we'll just say our amplitude is +1. And then our range is directly related to our amplitude. Because we're just deviating by 1 from our midline of 0, we can still say on this one, as crazy as that question looked, that our range is just from -1 to +1, because it's inherently related to your amplitude. Now that would change if we vertically shifted it up and down, like if we moved it up or down, that would change the range, but we're not there yet, so don't worry about that for now. For now, we can consider the range directly connected to our amplitude. As for the period, remember the period in degrees of a normal sine or cosine function is 360 degrees. But we need to multiply that by a horizontal stretch to figure out your new period, because again, you're horizontally stretching all of your x components by 1/6. So it's going to become, it's going to become a lot tighter, right? It's going to become a much tighter wave. So you can just take 360 and times it by 1/6. 360 times by 1/6 is actually 60 degrees. And we can do the same thing with our period in radians. And again, our period in radians is 2 pi. So 2 pi times 1/6, you consider as 2 pi over 6, but it's better to simplify that down if possible, which does work, 2 pi over 3. And boom, that shouldn't be a big surprise, because hopefully you remember from chapter 4, 60 degrees is the same thing as pi over 3 radians, right? So those are the exact same angle. That actually works quite well. Last question we're going to do here, 6 cos -1/3 x. Holy smokes. All right, let's look at all the things that are happening on this. We have a 6 on the outside. That's a vertical stretch by 6. What you see for a vertical stretch is what you get. It's not like horizontal stretches where it's backwards. Now, horizontally, we not only have a 1/3 in here, but we also have a negative. So I'll start by addressing that negative. It's a horizontal, not stretch, horizontal reflection. But then we also have the horizontal stretch, not by 1/3, horizontal stretch, not by 1/3, but rather by the reciprocal of 1/3, which is 3, okay? So let's now look at our amplitude and our range. Our amplitude in this case is going to be 6 because it's our vertical stretch. Amplitude is 6. And then as for our range, again, because we're not moving this up or down, we can say our range is from -6 to +6. As for our period in degrees, remember originally it's 360. You just need to times that by, of course, your horizontal stretch. Now, even though we're horizontally reflecting that, that's just going to make a mirror image of it. It's not going to affect the period by having a negative horizontal reflection on this. So instead, you can just still look at your horizontal stretch. It's not the end of the world. So either way, we got to go 360 times 3. 360 times 3, I'm pretty sure, is 1080 degrees. So that is your new period in this case. And your period in radians, again, you're just comparing it to 2 pi. So 2 pi times 3, that's a lot easier. That's just 6 pi. Okay? So therefore, we could also say 1080 degrees is 6 pi if you were to convert those. Whew, okay, so in summary, I know that was a very long lesson, but it's quite an intro to this unit, and this unit is a big one. So sine and cosine are periodic functions that take the appearance of a wave. When x equals 0, sine is 0 at the midline and is going up. And cosine x is at 1, it's maximum and about to go down. So again, basically it's just saying sine starts at your midline going up like that, whereas cosine starts at your maximum going down like that. Right? Otherwise, they're the exact same thing. They're still a wave. It's just they've been shifted one way or another. Cosine, you just moved like sine over to the left. Or you could say sine, you just took cosine and you moved it to the right, or whatever you want to talk about it with, right? It's still the same thing. Now, the period of these functions is 2 pi radians or 360 degrees, assuming nothing was ever, horizontally stretching it. Now, the height above the midline is called your amplitude, and it's directly equal to your vertical stretch A. And the wavelength, okay, I didn't call it that today, but you could consider it a wavelength, is called the period, and it's related to your horizontal stretch B, in that the period is 1 over B, or in other words, your horizontal stretch times by 2 pi. Or you consider it B is 1 over B, period is 1 over B times 360 degrees. Again, 1 over B is your horizontal stretch. That's why I kind of just like paused there for a second. I don't like how I said it's related to your horizontal stretch B, but your horizontal stretch is 1 over B. B is just the value in that equation. That's all, right? So don't get confused by that. Your horizontal stretch is not your B value, it's 1 over B. Anyway, we're done. So for practice, and it is absolutely essential that you get some of this practice in here, I want you to do page 233, questions 4 to 11. If you see a question that's too easy, move on. You don't have to do it. Again, as always, if you have any questions, please email me, send me a reminder, whatever you need to do. Best of luck.